Exponential functions can be used to model growth where the rate of growth is proportional to the current size. And this, of course, is called exponential growth. So the general form of exponential growth is this here, y equals a, some number, times e to the bx, where b is some positive number. And, of course, e is the natural base, 2.718, and so forth. So this is our exponential growth model, and we can use it to model really any situation where we have, again, a growth that's proportional, whose growth rate is proportional to its size. So looking here at an example, the amount S in billions of dollars spent in the United States on mobile online advertising in the years 2010 through 2014 are shown below. A scatter plot of the data is shown as well. We would like to find an exponential model for this data using t equals 0 for the year 2000. We're going to use our calculator to do this. We're going to do a regression model with this data here. So we're going to go to our data sheet, okay, and we're going to go ahead and enter these values. Now, it's, of course, S and then and the year. I'm just going to call them X and Y just so that because I know that I'm very comfortable with X's and Y's. Okay, so for our X, those are our years. So we've got, I guess maybe I should use T since we're doing T equals 0. Let's go ahead and do T. So our T values, when T is 0, we've got 2010, and so we're going to, we've got 2000. So 2010 it will be T equals 10. So we've got 10, 11, 12, 13, and 14. And then we've got our S values, the amount spent. And so we've got 0.6, 1.6, 3.4, 7.1, and 12.5. Now we'd like to get an exponential model for this. So I'm going to go to Menu, Statistics, Stat Calculations, and then we're going to do an exponential regression. Okay, so exponential regression right here. And we've got a lot of different options here, but we're just going to go ahead and put in our X list. Our X list is, of course, the T column, and the Y is Y. And this is going to be our exponential model. So here we have a model, and you'll notice that it has a times b to the x. And that actually, it doesn't look like our standard model. Our standard model we know is a times e to the bx. And it's important to realize that these are actually equivalent for, you can change the value of b, and then, like we could write this as a times e to the b to the x. Okay? And so some calculators will give you a model that is kind of this form, right? A number times another number to the x. And that's what we have right here. And so our model is, y equals A is 0.000355, 0.00355, and then times, and then this whole number to the x in the formula is 2.13. 2.13 to the x. So this looks a little bit different than the e to the bx, but that's okay. It's still an exponential model. Now, using this model, we can find some values that would be estimated for these years, and so we're going to go ahead and type some of those into the calculator. So I'll just go ahead and do a calculator here and do some of these values. So I've got 0.000355 times 2.13 to the 10. That would be for my 2010. You'll see, well, it gives me 0.68, which is, well, close to 0.6, but of course not the same. And we can do the same thing. We're just going to go ahead and copy that, but now in my exponent, instead of 10, I'll put 11. Okay. We get 1.45 again, close to 1.6, but not exact. Go ahead and copy that, and we'll put in our exponent of 12. So 3.096. Again, kind of close to 3.4, but not exact. And of course, we can go through and do this with all the different values. And what we see is that while we do get some approximations, okay, it's not perfect. Now you'll notice that most of these numbers that we got were a little bit smaller. Like these ones in the middle were a little bit smaller than the observed values, okay, what our model would predict. Notice that for 2014, okay, we get, raised to the 14. It actually jumps quite a bit. It's quite a bit higher than the 12.5. And so, kind of out on the edges, it was a little bit higher, and inside it was lower. And so, of course, mathematical models are not perfect because they're just estimating based on the trends that we see. Now here it says, according to the model, what year will the amount spent on mobile online advertising be? Approximately 65 billion. So now we're just taking 65 and setting equal to this, because this was, again, in billions. So we're just setting it equal to our model. And then we'd like to solve for x. So if I divide both sides by this number here, 65 over 0.000355 equals 2.13 to the x. To solve for this x, I need to use a logarithm. And I'm just going to do the natural log of both sides here. So natural log of 65 over 0.000355 equals, and now when I do the natural log over here, that exponent of x can come out in front. Okay, so I'm going to go ahead and pull that out in front. All right, then I can divide by this natural log of 2.13, and that will solve for the x. Okay, I guess I should be calling it t, because that was when t equals 0. That was not very precise on my part. So divide natural log 65 over 0.000355 over the natural log of 2.13. Let's go ahead and put that here in our calculator. So we've got our natural log of 65 over 0.000355, and then over the natural log of 2.13. We get about 16. Okay, I'm just going to go ahead and that's about 16. So this is an approximation saying we're expecting in the year 2016 that we would have that much 65 billion spent if this model is accurate.